It's math time, everybody. Problem 1. A basketball player makes 80% of her free throws. Suppose she takes 60 shots. So, the N is going to be the number of trials, so that's going to be 60. P is the probability of success, which is 80%, so 0.80. And then 1 minus P is the probability of failure, so it's just the opposite. For B, the mean is going to be 60 times 0.80. It's N times P. That's 48. That's the expected number of successes. The standard deviation is the variability of successes around the mean. And that's going to be, so it's the, what is it called? The square root of 48, so mean, times 1 minus 0.80, and that's going to give you 3.1. And then on to question 3. Alright, so it's just asking if normal approximation can be used, and after doing this, it can be used, because NP, or the mean, is 48, which is greater than or equal to 10. Well, it's greater than 10. And then N times 1 minus 0.80 is 12, and that's larger than 10. So yes, it meets the requirements. And then the probability that she makes at least 50 shots, that's going to be x minus the mean divided by standard deviation. But with the continuity, with the, I think it's called a continuity curve, you're going to subtract 0.5 from 50, just to make it more accurate. So that's going to be 49.5 minus 48 divided by 3.1. And that is 0.48. And then, but there's more. If you go to the Z table, you're going to find 0.48, and then that equals 0.6844. And then the last step is you got to do 1 minus 0.6844, and that is 0.3156. And as you can see right there. Right there. Cool. All right. So the normal model. Yeah. For part 5, it's why do statisticians sometimes use the normal model for binomial probabilities, even though it's only an approximation? That is because when mean and N1 minus P are large, the normal mode is convenient because it uses the Z table and all of that helpful stuff, and it gives reasonable approximations. Okay, question 2. The mean is just going to be 60. It doesn't have to change at all. But the standard deviation, you need to put that into standard error. And to do that, you do standard deviation divided by the square root of the sample. So that's going to be 12 divided by the square root of 36, which is 2. For B, or part 2, what is the probability that a sample mean is greater than 63? This is easier than it seems. You're going to do 63 minus 60 divided by 2. That's it. So sample mean minus mean divided by 2. And that's 1.5. So you're going to go to Z-score and find the probability that matches this, and that's 0.9332. But this is all the left-hand tail. So you're going to have to subtract it from 1 to make it right-hand, and that's going to be 0.0668. So it has a 6.68% chance that a sample mean is greater than 63. And then what this is going to look like is this right here. So this at 63 is a sample mean. This is the population mean. So all that is to the right of the sample mean, that's going to be the shaded in area because it's greater than 63. For part 4, the central limit theorem is useful in this because 36 is a large sample size, and using X bar makes the distribution normal. With larger samples, the sample distribution gets more normal. So it's a good thing that we're using it here because 36 is a larger sample size. It just makes it easier. Yeah, okay. And then for E, or part 5, if the sample size increases to 100, X bar is going to be smaller. Standard deviation is going to be smaller, like standard error. And because of this, it's going to be more accurate to the population mean, which is 60, because there's less variability. And that's similar to part 6, because the law of large numbers says that with larger samples comes more accuracy to the population mean. Yeah, so X bar becomes more accurate to the population mean because the sample is larger. Question 3. Number 1, 95% confidence interval for the population. Okay, so to do this, you have to find the standard error, and with the information provided, that's standard deviation, which is 0.40, divided by the population, or the square root of the population, so that is going to be 0.057. For a 95% confidence interval, that z-score is 1.96, so you're going to do that times the standard error, and in this case, that is 0.112. And then to find the interval, you're going to go to the mean, or the average GPA. So that's 3.15. You're going to subtract 0.112 from it and add it. So the answers you get for that is 3.038 and 3.262. So you're going to just put those next to each other as intervals, with the smallest one first and then the largest one second. So this is the confidence interval right there. All right. So what does this actually mean? For it to have a 95% confidence level, that means we are 95% confident that the true mean GPA of the population lies between these two numbers. But we'll get into if it's a different confidence level. Okay, so a sketch of this example would be, it's kind of bad and small, but so I have that right there, and see how most of it is shaded in? That's because it's a 95% confidence interval. But basically, if you have 3.0, what is it? 3.038, and then you have 3.21 and then the 3.15 in the middle, you just shade in that area between. Now okay, so for a 99% confidence interval, using the same data, it's going to be a little different. So to find z-score, you're going to do, so there's 99, and then right and left tail, that equals 1. So you're going to do 99.5, because 1 divided by 2 is 0.5. So that isn't going to be 1.96, it's going to be 2.57. So you're going to do the standard error, 0.057 times 2.57, that's 0.146. So again, do the same thing, 3.15 minus 0.146, 3.15 plus 0.146, so that is going to be an interval of 3.004 and 3.296. Now this is an even bigger width, not by too much, but this width is 0.292 apart, and the other one was 0.224. So increasing the confidence level increases the width. Now going back to the 95%, but changing the population mean, the sample, the N, to 100, you're going to do the exact same thing, except it's going to be a different standard error. It's going to be 0.04 times 1.96, and then add and subtract the answer from 3.15, and your answer is going to be 3.0716 and 3.2284, just like that. All right, so with the smaller population size, the width was 0.224, but now it's 0.1568. So when you increase the population, or you increase the sample. When you increase the sample, then the width decreases. And that kind of just answered F. It's just bigger sample that you have, there's a smaller width. Bigger confidence level, it increases. Number 4. Okay. Number 1. State the null and alternative hypothesis clearly. Okay, so with the information that we have, they believe that the mean is equal to 12 ounces. So that's going to be your hypothesis. It's H, and then a little tiny like 0 thing. It represents the null. So that's going to be mean equals 12 ounces. Now, the contradiction is they believe, like some people believe, that the mean is less than 12 ounces. So what you're going to do for that, you're going to do H and then a little X thing. It's like the alternative. And then open the mouth at 12. So this is one-sided because it's only talking about less than. If it was equal and then a little dash, then it would be two-sided, but it's one-sided this time. So to compute the test statistic and find the p-value, what we're going to do, the formula is z equals x bar minus the null hypothesis divided by the standard error. So what you're going to do for that is the x bar in this case is 11.92 minus the null, which is 12, divided by 0.24, which is the standard deviation, divided by the sample, which is, or the what's it called? Square root of the sample, which is the square root of 40. So that in all equals negative 2.11. And then you're going to go to the z-chart and find the probability, which in this case is 0.0174. So here is all of that written down, just as sample that I actually did it. Okay, and then for C, at 0.05 significance level, what is your conclusion? So 0.0174 is less than 0.05, which means that the soda is less than 12 ounces, which means that you also have to reject the null hypothesis. And this is what that's going to look like on a graph. You can see here, it's the, this is the rejection site. This is the mean, this is the x bar, and the z-score. And then lastly, for this one, so what does the p-value represent in this situation? It's basically the probability that the null hypothesis is true. And since it's very small, it's most likely that the null hypothesis is not true. And in this case, we found out that it's not. It can be rejected. So usually when there's a smaller p-value, there is stronger evidence against the null hypothesis. For number 5, the first part, according to the data, it's state the null and alternative hypothesis. So the null is going to be just the mean is 200, and the alternate to the null is going to be mean is not equal to 200. It's just going to have an equal and then a dash in it. That's what it looks like right there. And this means that it's two-sided because it could either be like, it's just, this could be any change. It's not like it has to be a lower change or it has to be a positive change. It's just any change. So yeah, so compute the test statistic with the data and the degrees of freedom. Literally, degrees of freedom is the easiest thing. you just do the number, like the sample number, minus 1. So in this case, it's 15 minus 1, so that's 14. And then the t-value, you're going to do x bar, which is 194 minus 200, divided by 20, divided by the, why do I always forget this word? Square root of 15. And that's just a formula. You just plug in the numbers. That's going to give you negative 1.16. So that's the test statistic. And then for the third part, find the critical value for t, test at 0.05 with your degrees of freedom, decide whether to reject or fail to reject. Okay, so for this you need a t-chart. Basically, all you're going to do, you're just going to match it up. So you're going to go to degrees of freedom, which is 14, and then you're going to go to 0.05 for the two-tailed, and just, boop, that's your answer. So that answer is 2.145, and that is greater than 1.162, which means we're going to fail to reject the null, because it's greater. So what this is going to look like on a graph is this right here. See how it's two-tailed? And then you're going to do your 2.145. Yeah, one's going to be negative, one's going to be positive. This is the fail to reject zone. Here's the 0 right here. And then, yeah, you just shade in these other. If the answer was in here, then we would reject the null. But since it's in between, we are failing to reject the null. And then construct a 95% confidence level. So before you do this, it's similar to one of the questions that we did before, but this time you're going to use that same number, 2.145, except you're going to multiply it by the, you're going to go back to your t-table, go back to 14, and find the 95% confidence level. Yeah. And that is going to give you, oh wait, just kidding. 1 second. I know it's 5.16. Let me figure out how I got that. I forgot how I got that. Oh! Never mind. Okay, so, scratch what I just said. You're going to go to the 95% confidence level and then match it up with 14. And that's going to give you 2.145. The 5.16 comes from the, just comes from the 20 divided by the square root of 15, which is the standard error. So you're going to multiply those, you get 11.07. So you're going to do the same thing, just 200 plus and minus 11.07, and that gives you this interval right here. It's 188.93 and 211.07. And 194 is the X bar, and that falls in the no reject zone because it's between these numbers. So that's how we know we reject it. And then lastly, explain how inference using the t-distribution for a population mean is similar to and different from the z-based. Yeah, so basically how it's different is for the t-values, S is used rather than standard deviation, because typically we don't have standard deviation for S, or for t-values, while the Z uses standard deviation instead of S to find standard error. And then they're similar because they both use confidence level, and they're both used for hypotheses. Thank you for listening.